In this video, we are going to talk about switched LAN technologies. Ethernet limitations. Signals are graded with transmission distance. Each Ethernet type has a maximum segment length, which if you didn't know that, that's exactly 100 meters. A segment is a network connection that is made by a single unbroken network cable. Ethernet cables and segments can span only a limited physical distance beyond which transmissions become degraded because of line noise, reduced signal strength, and the failure to follow the CCNA CD design guide. That is going to be a way for you to prevent things from happening. So what do you do if you have a connection that's, say 150 meters or something like that, or a couple football fields? Well, you need to extend the Ethernet LAN segments. So how would you do that? Well, you could add another device, which will help you share the bandwidth, extends the cable distances. It can repeat or amplify the signal, and a number of repeaters and hubs is limited. Normally, you wouldn't use a repeater in a LAN environment where you're dealing with wired connectivity. Normally, you would use another switch, or if Ethernet typically is not going to be the answer for that anyway, I would use fiber optics. I would use a single or a multi-mode fiber if I know the span is going to be longer than 100 meters. So typically I use fiber, but fiber may not be available, and if it's not, I will utilize a intermediary device. I will try to, depending on the circumstance, I will try to use a small switch to get the connectivity to where I need it to be, but it really depends on the deployment. Now, when it comes to typically what you're going to see here is if you know prior to deployment that the run is going to be longer than 100 meters, I will try to use, wherever possible, fiber optic cabling. Fiber optic doesn't have the distance limitations that Ethernet does. Now, if fiber is not available or not able to be ran or whatever the case might be, I will try to put in a small switch in between the two locations. Or I will design the network in such a way where I'll split it up to where it'll be an MDF to an IDF to an IDF to an IDF, and they'll be daisy chained. Now, I normally disagree with that style of deployment, but sometimes you may not have a choice with the type of setup you're working on. So it really depends on the deployment, but at the same point in time, you need to try your best to limit fault domains and failure domains wherever you can. So whenever you're daisy chaining switches together and things like that, you can definitely cause a fault domain, because if, say, you've got a 5-switch chain of switches, so if you got 1 follows 2, follows 3, follows 4, follows 5, switch 3 goes down, switches 4 and 5 go down with it. So failure domains are something you should be trying to mitigate, not make more of. Now, hubs and collisions. We've already discussed this a little bit in the previous video when we talked about how hubs work and a little bit about what they do in transmitting and things like that. So stations can transmit simultaneously. Collisions can occur. The more that occur, the worse the condition becomes. So that's a situation where, if you have a situation where you are dealing with hubs still, you more than likely should not be, but in case you have to deal with that, then you'll have to deal with that accordingly. Now, the drawback to hubs is they cannot improve collision issues. So if you have more than 2 stations on a shared media transmit at the same time, collisions occur and the frames are destroyed. So, and as the bullet point reads, when the sending station recognizes the collision event, they will transmit a special jam signal for a predetermined time. The sending station will begin a random timer and must be completed before attempting to retransmit the data. Okay, that's all well and good. But the drawback, you've got to resend the data. You have to wait a period of time before you can send again. Now, let's assume that you've had a collision and then you're going to go ahead and you need to resend your data. Well, you turn around and you have another collision. So you have to stop again and you have to wait for the back-off timer to happen, and then you send again. This is very inefficient. So the way that this is mitigated is with switches. We've already talked about that a little bit so far. But let's take a little bit of a deeper dive into collision domains and broadcast domains. Now, collision domain. Network segments that share the same bandwidth are known as collision domains. When two or more devices try to communicate at the same time, collisions may occur. A broadcast domain. Devices that are able to communicate with each other that don't traverse a layer 3 device. All right, now, so let's talk about this for a moment. Grab my pen pad out real quick. So let's break down how this actually works out. We'll take a couple of minutes and break down collision domains versus broadcast domains, because I think that will drive the point home for most of you. So this in front of you, folks, is a switch. Okay, you've got a bunch of these little blocks in here are just Ethernet ports that you plug things into. Now the way this will work out is the switch will have a MAC address table. So what it'll do is everything on top here, so this is going to be all the odd ports, right, is on top, and all the even are on the bottom. Okay, now we'll do this will be 1, 3, 5, 7, 9, etc. You do 2, 4, 6, I'm sorry, 2, 4, 6, 8, 10. Okay, we'll do that. Now, in a hub, if traffic comes in on this port right here, then traffic is going to go out this interface, this interface, this interface, this interface, this interface, everything in the same VLAN. Well, unfortunately, hubs only work on one VLAN. That's VLAN 1. So that means that every port that's in that VLAN is going to receive it. So let's assume that all these ports right here are in VLAN 1. All these ports right here on this side of the switch are in VLAN 10. Okay, just if you don't know what a VLAN is at this point in time, that's okay. We'll get there. But a VLAN basically, a very, very high level, allows you to virtualize a switch. So basically it allows you to separate what ports on the switch are able to talk with other ports on the same switch or other switches. So VLAN 1 is the default VLAN for just about every vendor that I've ever worked with. Cisco, Juniper, HP, Brocade, they're all the same. So what I end up having to do here is you're connected here, and then everything goes out every interface on VLAN 1. Okay, now that's not very efficient, right? Well, what'll end up happening here is, let's say that we have ports 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Every one of these ports is plugged into a computer. So we learned MAC address A, B, C, D, E, F, G, H, I, J, and just go with it. I know the MAC addresses don't go that high, but just for the sake of argument, we're going to go that direction. Actually, let me do it this way. We'll go, and this will be A1, B2, C3, D4, just to make it relevant. So we have that. So once the computer talks to the switch will learn the MAC address that computer sent in. So now this is the CAN table. Port 1 knows about MAC address A, port 2 knows about MAC address B. The benefit to a switch is that this guy right here, let me switch over to a different color. This guy right here, this on a switch is a collision domain. This here on a switch is also a collision domain. All ports on a switch are a collision domain. No, what makes it a collision domain? Well, that's simple. This right here. The MAC address table, or the content addressable memory, or the CAM table. They're pretty much the same thing. It's where the MAC addresses are learned and stored during their time on that switch. Sometimes they time out, sometimes they get aged out, whatever the case might be. But at the end of the day, there is actually a default time limit of 5 minutes, but you can adjust that. So you have that. So this is how a switch is able to determine what's going on. So now a collision domain is on a per port basis on a switch. So if I receive on port 1, if port 1 receives in a destination frame in the layer 2 header, say the layer 2 header looks like this. We have a source and we have a destination. Let's say the source is computer A or computer the computer attached to port 1 wants to send something to computer on port 5. So the source, the source address here is going to be A. The destination is going to be E. See how that works out? Now the switch is going to look in the CAM table and say, okay, the destination is MAC address E. So he's going to look at the CAM table. He's going to say, oh, well, I've got a match entry right there. So now all I have to do is move him from here to here. Now this assumes, and this is why I haven't covered broadcast domain yet. This assumes that port 1 and port 5 are in the same broadcast domain. And you're like, okay. Well, the broadcast domain is not the same as the collision domain. A collision domain is going to limit what can happen on the switch port. So since every switch port knows that there's going to be a mapping for the port to the MAC mapping, so that when an incoming frame is received on the switch port, the destination MAC address is looked at, and then if it's inside the CAM table, you know where to send it, whether it's on the same switch or maybe potentially on a trunk link to another switch or to a router. Now, with that being said, a broadcast domain is a little bit different. Broadcast domain is going to be subnet specific. Now, we haven't really covered this too much because the way that this works out is all of the words that I'm writing on the screen, broadcast, subnet, VLAN, they all mean the same thing. So a broadcast domain equals a subnet equals a VLAN. So let's say, for instance, your broadcast domain is 10.1.1.0/24. We've already covered subnetting, so you should be familiar with at least that much. A subnet is what this guy represents. This is a subnet. Now, what you do when you configure VLANs is you go in here and you configure a VLAN number, and most of the time you configure a name to go along with it. So let's say VLAN 1 is data. I highly recommend you don't use VLAN 1 for anything data. It's up to you on how you want to do that. So let's say, for instance, that's the case. And let's say that right here, this octet right there, this third one right there, that indicates your VLAN number. So maybe you've got VLAN 2 is 10.1.2.0/24. Now, this is an indication of a broadcast domain. A broadcast domain is not limited to the port like the collision domain is. A broadcast domain is limited to whatever ports have been applied to that VLAN. So it scales, right? So in this case over here, we've got all 10 ports are in VLAN 1. They're all in the same broadcast domain. So that means if 7 wants to talk to 6, he can do so. If 8 wants to talk to 3, he can do that. If 10 and 9 want to have a conversation with each other, go right ahead. Now, I split this switch in two. I've got VLAN 1 and I got VLAN 10. Now, from what you know about networking, do you think that a port in VLAN 1 can talk to port 11 in VLAN 10? If this was a live class, I'd poll the class, but it's not. It's a pre-recorded. The answer to your question is no, it will not. At least not on the same layer 2 switch. Now, how can we fix this? Well, you do what they call either layer 3 switching or inter-VLAN routing. Now, I don't want to get too far ahead of myself here, but the general idea here is this. If this switch has been configured with two different VLANs, VLAN 1 on the first 10 ports, VLAN 11 on the back 12 ports. Let's say it's a 22 port switch. That's what I chose to draw. So what'll end up happening here is this black line right here, which I'm going to basically put a very long narrow circle around, is the division point in that switch. Now, by looking at the switch from a front-facing view, you wouldn't be able to tell that. That switch would look, all 24 or 22 ports in this case, would all look the same. They'd all be ports, they'd all have cables into it. Configuration-wise, the way the ports are configured on a per-port basis would determine that. So by doing this and creating a VLAN, you've then created a broadcast domain. Now let's draw out a couple switches. We have another switch here, we have another switch here, another switch here, and then, that's a horrible switch, but anyway, you get the point. And then we have a cable connecting each one of these guys together. And then we go up here, we have a router. So this guy here is going to be our VLAN router up here. So anything that we want to correlate, we can. So let's say, for instance, this guy up here it's broken into 3 VLANs, 1, 10, and 20. This guy here is, 10, 20, and 30. This guy is 30, 10, and 2, for sake of argument. Now, what will end up happening here, from a configuration perspective, whatever ports in VLAN 1 are configured for VLAN 1 will only be able to talk with VLAN 1. And that's on this switch, and this switch. Okay. Now, I've got VLAN 10, and I've got this switch can talk in VLAN 10, this switch can talk in VLAN 10, and so can this one. Now, why can they talk to each other but VLAN 1 cannot? Well, the answer is actually really simple, because there's no other switches configured with VLAN 1. So let's say, for instance, you got just a couple of ports in VLAN 1. Only these 2 ports will be able to talk to each other. Unless, of course, they send traffic up to the router, and then the router routes them from 10.1.0/24 to 10.1.10.0/24, or something like that. Whatever the subnet range is irrelevant. You can apply whatever you want to whatever VLAN you want. But the ability to talk to each other is going to be the main point. So you have a situation like that. Now you take that a step further. I have a computer here in VLAN 10 that wants to talk to this guy over here. Well, the way that happens is the MAC address table. So this switch right here knows, I'll say this is switch 1, this is switch 2, and this is switch 3. What will end up happening is switch 1 will know all of its MAC addresses for switch 1, switch 2, and switch 3. Now why does it do that? Because of the fact that it's all the same layer 2 area. Now, even though this guy up here is the layer 3 segmentation, all these layer 2 switches are layer 2 switches, which means they only forward based off of MAC address. That's all they care about. So this guy right here is a trunk, and this guy right here is a trunk. The lines that are interconnecting these switches are trunk links. That allows the intercommunication between the switches. So what will end up happening is if this computer here wants to talk to this computer here, he can do that. All he has to do on this switch is say, okay, I want to send to MAC address A1, and I have the MAC address of B. Well, okay, this switch right here is going to say, let me look in the routing or the MAC address table. Let me find MAC address A1 and what port I learned that MAC address in on. Well, in this case, it's going to be the trunk link, right? Because that's where, if he doesn't show MAC address table for that particular MAC, he's going to find it, and then that's where he's going to want to go. So then he forwards his traffic to the trunk. Now, we haven't gotten into trunking and VLANs and all that stuff yet, but this guy right here, he gets a .1Q tag as he goes down here across the trunk link. When the switch receives it, it looks at the .1Q tag, and the tag is tag 10. So that switch 2 knows that this incoming frame needs to get placed inside of the VLAN 10 network. And then it is dropped off. It's carried through the backplane of the switch and dropped off here at this port right here based off of the MAC address table. That is how that all comes into play. So as you can see, a collision domain prevents these ports from receiving traffic if they don't need it. If they're in the same broadcast domain, that will extend the amount of ports that they can talk to, on which switches they could talk to, but because the fact that these ports are individual, and because the fact that there is a MAC address table, a database for the switch to refer to when it comes to forwarding traffic, there is no collision anymore. Unless, of course, let's say, for instance, the MAC address total of this switch is 4,096 MAC addresses. If this guy has learned 4,097, well, guess what? That new MAC address that he just learned is broadcast everywhere, because there's no more room to learn mappings in the MAC address table. It's full. So he has to resort back to hub-like behavior, which is sending it everywhere. I don't know where to put, I don't know where you came from, I don't know where you're going, so I'm just going to send you everywhere. Unless, of course, there's there's a hacker that maybe used a program to flood a bunch of randomly generated MAC address table or MAC addresses. I have seen that in the past. I've actually demoed that a couple times just to see what it would look like. Doesn't take long to fill up a MAC address table on a lower end switch. So especially like a 2950 or like a 3550, those guys don't have a whole lot of RAM on them, so they don't have a whole lot of database. So that just gives you an idea of how that would work. So now we've covered collision domains and broadcast domains, and I hope that really helped visualize how that would work out. Our next thing to talk about is going to be switches and bridges. Now, switches and bridges are kind of unique because of the fact that the bridge acted as a way of getting traffic from one part of the network to the other. So a hub, device for connecting multiple devices together and making them act as a single network segment. It's not used anymore for obvious reasons, as we've already discussed. Switches themselves, switch characteristics, well, they have a high port density. Typically, 24 and 48 port switches are common. That's not the only port density that come in. If you go into the data center, you might only get 32 ports because they might come in 16 port blocks, whatever the case might be. They had varying speeds, and that's one of the other kind of cool things, that there's a mixture of speeds. So one port could be 100 meg, the next port could be gigabit, the trunk link up to the other switches could be 10 gigabit. They have different variations of how you would do things. They support large frame buffers. Now the buffers are going to help when it comes to forwarding capabilities, and we'll talk about that in the next slide and how that actually works. But the idea of it is, the bigger the switches, the bigger the buffers are going to be, the more forwarding capabilities that they have. Now, when it comes to the actual setup of switches, there's 3 different ways that switches actually switch. And the same thing will all happen when we get into routing and how a router will switch the traffic between the interfaces. For right now, let's just focus on the switch. They have fast internal switching. So there's 3 different types. You have cut through, store and forward, and fragment free. The major differences between them. So cut through is going to immediately start forwarding the data as it is received. There's no error checking done. Store and forward is going to store the data in buffers until the whole frame is received. The destination is recursed and forwarded. Error checking is performed. Less likely to have an error. Now, you might say, okay, well, how does that work? Well, the way this works is, and it actually goes back to the buffers here. The bigger the buffer, the bigger the frames, or the more of them you can hold in your at the port level. Now, one of the things that I want you guys to be aware of is all the stuff that we've been talking about so far. We haven't gotten into the components of a switch, like the RAM, the ROM, things like that. But when you're receiving traffic in and you're holding a frame in the buffer, that buffer is actually made up of RAM. So every port gets a certain amount of RAM allocated to it for doing its job. And if it has enough RAM, enough memory allocated to it, it'll store those frames in memory until the recursion process takes place, which is what we're doing here with store and forward. With cut through, it's not quite as labor intensive on the switches part to forward the traffic, because of the fact that the traffic is coming in, it's hitting the port, and all it does is it looks at the layer 2 header, looks at the destination MAC address, looks in the routing and the switch on the MAC address table, and forwards the traffic on. That's literally all that happens. Now, at store and forward, it does like it says. It stores the whole frame in the buffer in memory. It recurses to figure out what to do with it, and then it sends it on, doing the error checking as well. Now you have fragment free. So basically, cut through switching provides low latency. So what it does is it's a kind of a mixture of both cut through and store and forward. So what will end up happening is the first 64 bytes of a frame are going to be stored in memory. What will end up happening is that 64 byte frame will be received in, error checking will be conducted, and if nothing is detected out of the ordinary, the traffic is forwarded on. So if frames can still be forwarded that are bad, because it's only subjected to the first 64 bytes, and after that, anything else that happens goes on from there. So if you have, and typically the way that this works out is the first 0 to 64 bytes anything 0 to 63 is anything that happens in that first portion is considered to be a collision. So when we look at the interface statistics and you look at the show interface statistics of an interface, you'll see these collisions, you'll see late collisions, things like that. A collision typically happens within the first 64 bytes. Now, if it doesn't happen in the first 64 bytes, it doesn't get detected by fragment-free switching. And then it goes beyond that, 65 through how many other bytes are left in that frame. Now, anything that happens 65 and beyond is considered to be a late collision. Now, you see late collisions, that means things is happening after the packet's been buffered and sent on. Now, typically when you have collisions, you're dealing with a duplex mismatch. And we'll talk about that later on when we actually get into the interface statistics. But we haven't really discussed duplex too much yet. But and we'll talk about that when we get into trunking, because that'll make a lot more sense then. But the idea with collisions, or with duplex, is half duplex means you can only send and then receive. You can't send and receive at the same time. Where full duplex means you're sending and receiving at the exact same time, and so the sender can send and receive at the exact same time. So basically it's bidirectional communication all the time. Now, network congestion is a big deal because of the fact of what it can do. With increasingly powerful computer and networking technologies, high volume of traffic, network traffic, and high bandwidth applications, it's typically network congestion is going to be seen, and you're going to have these issues, what they call microbursts. Now, what a microburst is basically is a burst of data that hits a switch port, or a router for that matter, and it comes in at way beyond the speed that it was supposed to come in at a certain period of time. So it may not be detectable, 5 minutes after it happened, but maybe you have a bunch of people trying to send data to the same server, or trying to request things from a server at the same time, and that server has to all of a sudden just rifle a bunch of stuff out and try to keep up with the requests. Well, that sudden surge of activity is typically referred to as a microburst. Now, microburst can cause packet loss, and typically is going to be something that happens microsecond. It happens within a 2 to 3, 4, maybe 400 millisecond period of time, which is roughly 2 tenths of a second, 4 tenths of a second, something like that. That's where those issues usually come into play. Now, the other thing that you can have in congestion, which may or may not actually be congestion, is when you have situations where you have delay-sensitive traffic. So what is an example of delay-sensitive traffic? Quality of service is a great example for one. Now, with quality of service, quality of service is how you would handle that. I'm sorry. Voice over IP is what I meant to say. Voice over IP is an example of a delay-sensitive type of traffic, where if I'm on the phone and I'm trying to send data, the packets that are actually encapsulating what the words that are coming out of my mouth right now that you're hearing are essentially voice over IP, and so they're being expelled from my mouth, and at that point they are hitting the network cable and they're being transmitted. Well, unfortunately, they don't have a whole lot of time to get to where they need to go, because when I'm talking on the phone to somebody, I want that traffic to get there as soon as it possibly can. Sub 100 milliseconds, typically. Anything longer than that, you start to notice things. If you're, depending on how good the network is and depending on how good your hearing is, you could start hearing or it'll sound like you're missing something, maybe a little garbled. You might get something that's out of order, where you might be trying to say, CCNA service provider, but it actually Urban Ire. It comes in all kind of goofy, and that's an example of drop packets. Network congestion can be a cause of that, and quality of service is typically how you would handle that. Now, in most cases, quality of service is actually relatively easy to put in play, and we're not going to talk about that too much until we get into the CCNP, but just be aware that those things can happen. And you also have high bandwidth applications that are sending a lot of data all day long, or high bulk data, FTP, things like that. Now, Ethernet bridges are unique in their own right. They operate at layer 2 of the OSI model. They forward, filter, and flood frames, sort of like what a hub does, but they only have a few ports and they lack high performance. So all they were designed to do was to interconnect different areas of the network together. That was it. They were just a layer 2 forwarding device, and that was pretty much it. So not a whole lot more I can really go in on bridges. The main thing you want to be familiar with, and why I'm spending more time on it, is Ethernet switches. They have a high port density, 24, 48 ports typically. Large frame buffers. So if you're going to be sending a lot of data, you have to be able to hold all that data in memory while you do your error checking and then send it out the wire. Mixture of port speeds. You can have one port that's at 100 megs, another one that's a gig, and another one that's a 10 gigabit. As long as the switch supports it, you can do it. Fast internal switching. You can have very, very fast backplane. So you could be switching, at near line rate the entire time. Now, depending on the situation, when it comes to switching, you can run into problems where you get into data streams that require line rate. Now, what do I mean by line rate? Line rate means that if the interface is configured for gigabit transmission, it can forward at 1 billion bits per second. That's what that means. So 1 billion bits per second are serialized to the physical cable and sent out the wire. That's what I mean by that. Now, depending on the switch, will determine how fast you can actually forward. So not every switch can switch at line rate. Your higher end boxes like Nexus, Catalyst 6500, those devices have the ability of performing what they call wire line rate forwarding. Now, some of your other switches, not so much. You might be able to get close to that. Typically, if you have like a 48 port gigabit switch, your backplane, which is going to be the interconnection between all of the switches, is going to be faster than that. And that the switches, what I mean by that is the switch ports, not the switches in general. The backplane is what's going to do what they call the fabric switching. The fabric switching is going to be port 1 and one's out to port 2. So there's what they call an ASIC, or an application-specific integrated circuitry. And what that does is that is going to be how the switches, or the switch ports, are going to be able to map to each other and figure out where traffic is going to go. So the ASIC is going to handle the layer 2 forwarding. Typically, that's all in hardware. So not too much that we can do with that, but we'll talk about how we could deal with switching later on when it comes to improvising that and some areas of improvement potentially. They also forward, filter, and flood frames, and do that with different mechanisms. You can do layer 2 MAC address filtering. You can do VLAN filters, things like that. Modern Ethernet switches. Dedicated communication between devices, multiple simultaneous conversations, full duplex communication, media rate adaptation. So you can have, as it says right there, 100 megs on a port gig 0/0 and 1 gigabit on gig 0/1. So it definitely depends on how you do things. Now, switching operation. How does this do what it does? The switch receives a broadcast frame from PCA on port 1. The switch enters the source MAC address and the switch port that received the frame into the MAC address table. So that's going to take the MAC address that was learned on that port from that computer. It's going to map the port it was learned in on to the MAC address that it learned. Because the destination is a broadcast, this is an example of how ARP works, if you didn't already know that. The destination address is a broadcast. The switch floods the frame to all ports except for the port on which it was received. What it's doing now is it doesn't know what to do with the destination. It doesn't know how to find it, or it doesn't know where it is, more specifically. It knows how to find it. It's what they call ARP. So ARP is going to go out there and say, okay, I've got this IP address. I know I need to find out what the MAC address is of 10.1.1.1. So what will end up happening is the destination device replies to the broadcast with the unicast frame addressed to PCA. So the computer that owns 10.1.1.1 says, oh, that's me. Here's my MAC address. That's what you need. So that information is then added to that switch. So now on whatever port that computer is located on is mapped to that MAC address. So port 2 knows about MAC address X. The switch enters the source MAC address of PCB and port number of the switch that it received on the frame into. The destination of the frame and its associated port is found in the MAC table, and the switch can now forward frames between source and destination without flooding. That is because it has entries in the MAC table that identify the associated ports. So that is what they call the collision domain. So I'm able to go in there, figure everything out, and know where I'm sending traffic. I don't have to sit there and think about it. I already know. All I have to do is look at the destination traffic, and off we go. Microsegmentation. So what this does is it eliminates the possibility of collisions on the network segment. Each device on the network segment is directly connected to a switch port. That is exactly how you prevent collision domains in a switch. You put every port in its own collision domain. You make sure that the MAC address that's entered in that port is entered in the MAC address table, and that is how you prevent bad things from happening to good networks. Modern LANs. Users are grouped by physical location. More switches added to the network. Switches connected by high-speed links. So this is basically how networks are put together. Typically, you're going to group your users by physical location, but that doesn't technically mean that if you have a bunch of users in the Milwaukee office that they all have to be on the same VLAN. That doesn't mean that at all. You might typically group them by department area. So if you have, let's say the HR department is located on the second floor east side, then that'll be the HR VLAN. That'll be the HR department. And then you have engineering. That'll be in a different department. And that's where users are typically going to be grouped physically, literally physically. But the switches that are in that network that are connecting each other are supporting multiple VLANs. Therefore, they can be configured as such. And then you can normally we configure this with either a like a stack-wise type of situation, maybe a Catalyst VSS for your chassis-based deployments, maybe a what they call VPC inside of, or I think it's VPC inside of Nexus, where you would bond the uplinks together and perform high availability wherever you can. Whatever the case it might be, will pretty much determine how you go about doing it.